The study of equilibrium in rigid bodies forms a cornerstone of mechanics, providing insights into how structures and systems remain stable under various forces and moments. In three-dimensional, 3D systems, equilibrium requires a more comprehensive analysis compared to two-dimensional cases, as forces and moments can act along or about any of the three Cartesian axes. In practical applications, understanding 3D equilibrium is essential for designing stable structures, such as bridges, buildings, and mechanical systems, where forces and moments act in complex spatial configurations. Engineers rely on equilibrium equations to determine unknown forces, reactions, and moments, ensuring the safety and functionality of the system. In three-dimensional space, a particle is in equilibrium when the vector sum of all the forces acting on it is zero. This means the particle does not experience any net force, resulting in no acceleration, Newton's first law of motion. To determine the unknown forces acting on a particle in 3D equilibrium, we will apply the principles of static equilibrium, which require that the sum of the forces in the x direction must be zero. The sum of the forces in the y direction must be zero. The sum of the forces in the z direction must be zero. If there are multiple forces acting on the particle, each force can be represented as a vector with components in the x, y, and z directions. Let's break down how to determine the unknown forces. Step 1. Define the forces acting on the particle. Let's assume that we have multiple forces acting on a particle. Each force can be described by its vector components in 3D. F1 equals F1x, F1y, F1z. F2 equals F2x, F2y, F3y. F3 equals F3x, F3y, F3z.
Step 2. Set up equilibrium equations. For each force, we can write its component in the x, y, and z directions. Now, we write the equilibrium conditions for each direction. In the x direction, F1x plus F2x plus F3x plus equals 0. In the y direction, F1y plus F2y plus F3y plus equals 0. In the z direction, F1z plus F2z plus F3z plus equals 0. Step 3. Solve for the unknown forces. If there are unknown forces, say Fx, Fy, Fz acting in the x, y, and z directions, we can substitute the known forces into the equations and solve for the unknowns. For example, if we know that F1 sad face Fx, Fy, Fz, unknown force, we can solve the equilibrium equations as follows. In the x direction, Fx plus other forces in x equals 0. In the y direction, Fy plus other forces in y equals 0. In the z direction, Fz plus other forces in z equals 0. By solving these three equations, we can find the unknown components of the force vector. Let's take a look at a problem and solve it to get a better understanding of equilibrium of rigid bodies in 3 dimension. The assembly shown consists of an 80 mm rod, AF, that is welded to a cross consisting of 4 200 mm arms. The assembly is supported by a ball and socket joint at F and by 3 short links, each of which forms an angle of 45 degrees with the vertical. For the loading shown, determine A. The tension in each link, B. The reaction at F. Solution. R, EF equals minus 200 I plus 80 J. T, B, equals T, B, I minus J, divided by square root 2. R, BF equals 80 J minus 200 K. T, C, equals T, C, minus J plus K, divided by square root 2. R, CF equals 200 I plus 80 J. T, D, equals T, D, minus I plus J, divided by square root 2. R, dE equals 80J plus 200K. Sigma M, F equals 0. R, BF, XT, B, plus R, CF, XT, C, plus R, DF, XT, D, plus R, EF, X, minus PJ, equals 0. Then we solve to obtain different equations. Equate coefficients of unit vector to 0 and multiply each equation by root 2. Equation 6 and 5 give us the tension Tc. Equation 6 gives us Tb. Equation 2 gives us Td. All tensions are obtained in terms of P. Equating all the forces to 0, we obtain the final force vector in terms of P, which turns out to be minus 0.345 pi plus pj minus 0.862 pk. Conclusion. Hence we have determined the tension in each link and the reaction at F. This problem gives us a good understanding of the concept of equilibrium of rigid bodies in 3 dimensions. The core concept that we have learned is, to determine the unknown forces acting on a particle in 3D equilibrium, we must apply the conditions of equilibrium, i.e., the sum of forces in each direction must be 0. By setting up the equilibrium equations for the x, y, and z components, we can solve for the unknown components of the forces. Thank you.